we're going to look at an example in R, and it's similar to the first problem that you had on the exam before spring break. We're going to be looking at EMTs using a randomized complete block design. So an experiment was conducted to determine if the type of bag, shoulder, or backpack, and bag weight, light or heavy, affected the time between steps of EMTs climbing stairs. And 21 local EMTs volunteered to participate in the study. Each EMT climbed a set of stairs under all 4 treatment combinations in a random order. We have 4 different treatments because there are 2 levels of bag type and 2 levels of bag weight. So 2 times 2 gives us 4. Since there are 2 factors and each participant was measured under all 4 possible treatments, we have a balanced 2-way randomized complete design experiment. So we're going to have our response variable yijk, the step time for the ith bag level, and the jth bag weight, and the kth EMT. So we'll have our overall mean mu, the effect of either the shoulder or a backpack, the effect of having a light or heavy bag, a potential interaction term between the shoulder and the backpack, and the light and heavy loadout, the effect of the EMT, and then the error term, because even with all of these components inside of our model, we're not going to get it exactly right. The big difference between the tree example and the EMT example is the tree example was a one-way complete block design, and this one is a 2-way complete randomized block design, because now we have 2 factors that are crossed, because both shoulder and backpack were used at the same time as light and heavy. So we have all four treatment combinations measured each time for each EMT. We have the data read in already, and we have 5 different columns: the subject or the EMT that participated, the overall load condition, whether they were using a heavy with backpack or heavy with shoulders, light with backpack, and light with shoulder. And then we have the factors kind of separate, whether they were using a heavy or a light loadout, and a backpack or a shoulder, and then the time in between steps on average for their ascent up the stairs. So it's always a good idea to do some initial analysis. So let's look at the averages for the 4 treatments. And if we're looking at heavy with backpack, the average step time was about 1.6 seconds. Heavy with shoulder, about 1.3. Light with backpack was about 1.3. And light with shoulders, about 1.3 as well. So as far as overall, the 4 different treatments, the only one that appears to be different is heavy with backpack. It seems to be a longer time in between steps in that configuration. If we want to look at it visually, we can look at different sets of box plots. So we can look at step time by bag weight. And it's kind of hard to tell because we have these outliers at the top and a single outlier up here. But overall, bag weights on average don't appear to be that different. Do the same thing with bag type. Overall, they appear to be pretty similar. And then looking at the 4 combinations of our treatments, the heavy with backpack is noticeably higher than the other 3. And then these other 3 appear to be pretty similar. Same thing that we saw when we were looking at the means. And if you just do load condition, the combination, we end up with the exact same box plots that we did for the previous one. What we can do is let's go ahead and remove the effect that each of the EMTs have. What you could do is go through, find the average for each EMT, subtract it from their 4 measurements, but that would be a bit of a hassle doing an R as is. What we can do instead is let's just fit an ANOVA model just by each subject. So they say the step time only depends on the subject that's being observed. We'll say that data is equal to EMT, so it knows where to find those 2 variables. So we'll fit a model with that, and we'll have 21 different means, 1 for each EMT. And then we'll just find the residuals. And these residuals are going to be the step times minus the effect of the EMT themselves. And so we'll store that as a new variable called the residuals of the subjects. And now we can redo everything that we did up here, just looking at each EMT effect removed from their step time. And what that does is it'll make the box plots thinner. It removes the spread of the EMTs themselves. And now it does appear to be a noticeable difference between the heavy backpacks and the light ones. Similarly, if we look at bag type, there appears to be somewhat of a difference between backpacks and shoulder. And then looking at the 4 treatment comparisons, the heavy backpacks appear to be noticeably higher still than the other 3 combinations. And the main worrisome one here is that this one appears to be wider than the other 3, which would violate our equal spread condition across the 4 treatment effects. That's something we'll check out later on. Another plot you want to make when you're dealing with 2 or more factors is we want to look at our interaction plots. So we can say with EMT, so it knows where to get the data. We want to create an interaction plot. Our X factor that will stick down here is bag weight. Our trace will be the bag type, so that's the lines it'll draw. And then our response is going to be step time. And if there is no interaction between the type of bag and the loadout, then these lines should be parallel. If this line is fairly flat, then this line should also be fairly flat. But there's a steep decrease going from heavy to light when you're using a 2-strap or the backpack type of bag. Whereas going from heavy to light with a shoulder doesn't seem to change it all that much. Since this line is flat for the shoulder, the heavy to light doesn't appear to be much of a difference. Since these ends of these 2 lines are close to one another, doesn't appear to be a difference between the backpack and the shoulder when we're dealing with the light. And since there's a large difference here, there does appear to be a difference in the heavy loadout versus the light loadout when we're looking at shoulders, or when we're looking at bag type between the backpack and the shoulder. There does appear a difference between the 2 when we're looking at heavy. And there does appear to be a difference when we're looking at the backpack style between the heavy loadout and the light loadout. So of our 4 treatment groups, it really only appears that one of them is different, and that's the same result that we saw when we aggregated them by mean. If you notice, all of these are about 1.3, 1.3 here, 1.3 here, 1.3 here. They're all about the same. The heavy backpack was about 1.6, and that's what we notice up here. So there does appear to be an interaction effect, and the only one treatment that appears to be different than the other 3 is heavy with backpack, since it's so far away removed from everyone else. How do we go about analyzing it with inference? So we'll fit a model, and right now we'll assume that the EMT is a fixed effect. So we'll say that M fixed sub for fixed effect by the subject, AOV our ANOVA model, step times our response variable, by the EMT themselves, the subjects, plus bag weight times bag type. So that way this includes an interaction effect between bag weight and bag type. Data is from EMT. And if we do a summary of it, there are 21 subjects. So that means our degrees of freedom for the subjects would be 20. Bag type and bag weight each have 1 degree of freedom. Each have 2 levels, so they should have 1 degree of freedom each. And then the number, your degrees of freedom for your interaction term is just going to be the degrees of freedom for each of those factors multiplied together. So 1 times 1 gives us 1. We have a total of 84 measurements. 84 minus 1 gives us 83. 20 plus 1 plus 1 plus 1 gives us 23. 23 plus 60 gives us 83. So we're back to our total. So all of our degrees of freedom are calculated correctly. If we look at our sums of squares, it seems that a lot of the differences in step time is based off the EMT, and that makes sense. Some EMTs will move faster than others. And the sums of squares for the bag type and bag weight appear to be pretty small. Not a lot of differences across them. We can calculate our mean squares for them, find our F values, and the interaction term is somewhat significant, and the 2 main effects are also somewhat significant. So it does appear that bag type and bag weight do play a role together anyway, since the interaction term is significant, in the time in between steps for these EMTs. When we were going through the slides, we mentioned that essentially what a randomized complete block design is doing is where for each one of the measurements, we're subtracting out the effect of that particular block. In this case, we're subtracting out the effect of the EMT. So if we fit the same ANOVA model, but now instead of doing a randomized complete block design on the step time, if we just do a completely randomized design on the residuals after we subtract out the subject's effects, so that's what this line is doing, and we run a summary on it, if you notice, everything stays the same except for the degrees of freedom. The sums of squares for bag weight is the same as it was earlier, for bag type is the same as it was earlier, and bag weight by bag type interaction, 0.346, the same in both cases, and the error for the residuals is the same, 4.896. The only difference is that we didn't tell R that we calculated our residuals by subtracting out 20 different means. So that's why these degrees of freedom are larger than they really should be. If we change this degrees of freedom from 80 to 60, then everything else would be correct. We'd end up with the exact same ANOVA table. And if we compare it to a randomized complete block, if we compare it to a completely randomized design where we ignore the effect of the EMTs, you can see that we get pretty different results. And that's because we took the sums of squares from our randomized complete block design. The effect of the subject got added in with the error terms. So 4.8 plus 4.9 gives us this 9.7. And because our MSE is now going to get a lot bigger, all of our p-values also get bigger. So all of the effects went from somewhat statistically significant to marginally significant because the EMTs had a large influence on their own step times. And then lastly, we can check our assumptions by using this plot function. And it's going to give you a dialog box down here. If you hit enter, we can see our residual versus fitted plots. A lot of the appears to be some additional spread. If you notice, there's a bit of a megaphone pattern indicating that there doesn't appear to be constant variance. Pretty small when step time is small, but the spread's pretty large the larger that our estimated step time becomes. And if we hit enter again, it'll bring up a QQ plot for trying to check normality, and doesn't appear to be that great because these tails deviate from the line fairly substantially, so there's some indication of non-normality in the residuals. We hit enter again, and it's going to give us our scale location. You want to remember that this line should be flat, and there does appear to be an increasing pattern in the line, indicating that maybe our constant variance assumption hasn't been met for our residuals. If you use the car library, there's some additional methods you can use to check our assumptions. If you do QQ capital plot, it'll fit the same QQ plot that the plot function does, but it'll add these error bounds, and if the dots are noticeably outside of those error bounds, that's a really bad sign for normality, and that's what we see here. We can do a Shapiro test. All you want to do is Shapiro.test, and then include your residuals in there. And you can see we get a really, really small p-value. So strong evidence that our normality assumption hasn't been met. But usually your normality assumption is the least concerned assumption that we have. If you have a large sample size, the ANOVA test is fairly robust against the non-normality of your residuals. The more important assumption we want to check is the equal spread. We can do that using Levine's test. And the problem that we have for Levine's test is it assumes the degrees of freedom are 80 and not 60. So it'll make the p-value smaller than it really should be. But if you go back to chapter 4, when we talked about how we go about checking our assumptions, we said Levine's test is essentially an ANOVA test. We just transform the data first. So what we can do is we'll just rescale it. Instead of dividing by 60, instead of divide by 80, we'll divide by 60. So we'll do Levine.f. You can pull out the f value from there, multiply it here. We end up with a new test statistic, an f value of 1.35. And our p-value from that is about 0.27. So while the plots didn't really look all that great as far as normality, as far as equal spread goes, according to our tests, there's no strong evidence that the equal spread condition hasn't been met. Normality hasn't been met, but that's usually okay as long as we have a larger sample size, and the equal spread condition, no evidence of it being violated. Since we rejected our null hypothesis, we want to see where those differences lie, so we want to follow it up with our pairwise comparisons. And we can do Tukey's on a significant difference in R, and since we rejected the notion that there isn't any interaction, we need to look at the pairwise comparisons, looking at all 4 treatments instead of just looking at the main effects. We can't compare the backpack to the shoulder bag or the light loadout to the heavy loadout because they're interacting with each other. So what you can do if you do Tukey HSD, fit in your model, and if you do this $, apostrophe, bag weight by bag type, end apostrophe, it'll just give you your pairwise comparisons for your treatment effects. With 4 different treatment effects, we should have 6 different pairwise comparisons. And if we bring back our interaction plot, we can kind of see what we should expect to get as statistically significant. This is the treatment of backpack and heavy loadout, and that appears to be the only one that's different from the other 3. Because if you notice, the other ones are a little bit higher than 1.3. These are 2 means are pretty close together. This mean and this mean are close together. This mean and this mean are close together. But the treatment effect of heavy with backpack are really far apart. And if we look at our pairwise comparisons, that's exactly what we get. If we're looking at light with backpack, light with shoulder, doesn't appear to be any difference there. Light shoulder, light backpack, really close. Heavy shoulder, heavy shoulder bag, light shoulder bag, those 2 really close. And then heavy shoulder, light bag, heavy shoulder, light bag are here. Those 2 really close, have a p-value of almost 1. It's this treatment up here that appears to be different from the rest. I couldn't figure out how to get R to do the means themselves for our 4 different treatments, so we'll just quote unquote do it by hand. And since we're treating the EMTs as a fixed effect, I'm basically looking at the means of these 4 treatments, of these 4 loadouts, on just these 21 EMTs. If I was working at a hospital, these are my only 21 EMTs that work there. Maybe I'm interested in these specific 21. So we want to find the standard error of our sample means. That's going to end up being our MSE. If we pull back up the summary, we see that our MSE of the residuals is about 0.08. And then we want to divide by the number of blocks that we have, because each treatment was measured a total of 21 times. We'll take the square root of it. So we end up with a standard error for each one of our treatment means of about 0.06 seconds. We can find our critical value. So if we're not doing any sort of multiple testing correction, we'll do QT, quartile for T, 0.975, our 5%. Divide by 2 gives you 2.5%, subtract from 1, so that way this is positive. Our degrees of freedom are 60, same degrees of freedom for our residuals. And then our confidence interval, we're just going to take the means, subtract out the critical value, times our standard error for the margin of error, add the margin of error, and that'll give us our confidence intervals. So we can be 95% confident that when they have a heavy loadout with the backpack, the average time in between steps is somewhere between 1.46 to 1.71 seconds. And for the other ones, they're all about the same, of about 1.8 seconds to 1.43 seconds in between each step. And we didn't do any sort of multiple comparison control, so each one of these confidence intervals is 95% confident individually, not overall as a whole. Let's say that I want to extend these results not to just these 21 EMTs, but to all EMTs. That means what I want to do is I want to treat them as random effects. So we'll fit the same model, but now instead of saying fixed sub, it'll be rand sub. The error terms of the EMTs, the same treatment effects, we're not changing those at all. And if we run the summary, we can see, and actually if we compare it down here, we'll end up with the exact same ANOVA table. And R is pretty smart. It knows that since each one of the treatments were inside of each EMT, that we want to put our effects of our factors with inside of the error ANOVA table instead of the EMT ANOVA table. When we're doing the nested effects, if each EMT was measured 4 times under the same treatment condition, then these would have been up here in this table. But again, R is smart enough to know where to place the factors, so it placed them all down here within the within error table. And the results end up being exactly the same. We end up with the same p-values, the same mean squares, and to where the main effects are somewhat significant and the interaction term is close to our significance level of 0.05. The problem, though, is if we want to go about extending these to creating confidence intervals, that the functions that we used above don't really like when you include an error term inside of the model itself. So we'll use NLME library so that way we can fit a linear mixed effect model. And the comparisons, we're going to use this multi-comp package as well. So you can go ahead and load both of those in. We'll use LME step time for the same effect of our factor. We want to include interactions, so we multiply them together. We want to tell them the random components. So random equals this tilde sign. So we're going to, this tilde sign 1 is going to basically fit a mean for each subject. So that's what this says. Add a random effect mean for each subject. Data is EMT, method is REML. Don't really have to concern yourself with that. And then if we do ANOVA.LME, you can see that we end up with the exact same results. So fitting the ANOVA table is the same either way, whether we use AOV typically or this LME function. But now what we can do is, since the interaction term is significant, instead of fitting them by their main effects plus interaction, let's just treat them as their own individual treatments. So we'll just do it by load condition. So we're essentially merging bag weight and bag type from 2 factors into 1 factor with 4 levels instead of 2 levels each. And this is going to allow us to find the estimates for our means. So we can create a confidence interval, the difference between bag type and bag weight combinations. So what this will do is find our pairwise comparisons. So this is going to be the load condition. You know what, fuck this. No one watches this anyway, so